Okay, Luke, let's try and do something different this week. So, my understanding, not that I've seen any evidence of it, is that you are a bit of a musical person.
Yeah.
So I think what we're going to try and do today is that you are going to try to explain something to me. You're going to explain music theory so I can understand
Right.
how music operates, and I don't have a musical bone in my body. So
I've heard you sing. So yeah. Okay, so here we go. Calling me a bit musical is probably still too much, but let's start at the start here. If you're my main point here is going to be two things. One, there really should be a music theory in here, because one of the points I'll be making is there's some choices we make along the way to music theory that we could have done differently. And the other one is, if you've got any sort of physicsy or mathematicsy sort of proclivities, music, there's a lot there to sink your teeth into. But let's get started. So, sound is a wave. Hopefully, we all know that. So, a certain frequency of sound. What we mean by that is, we see that sound is a compression wave, and the frequency is just how many of those wave fronts there that you can see goes past our eardrum every second. Let's call a certain frequency of sound a note. So generally we talk of the pitch of a sound as being related to its frequency. Even that's a bit of a simplification, but we're physicists, so we're going to simplify things anyway.
So may I jump in and ask a question?
Go for it.
So you say that sound is a wave traveling through the air, right? So when somebody plays a note, there's these waves traveling through the air. How come I hear a steady note instead of wah, 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 which is the wave, isn't it? Why don't I hear a wave? I just hear a steady.
So this is actually really interesting. Your body will hear, at low frequencies, your body will hear that sort of whoa, 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 but that's about 1 per second. And so this is interesting. The difference between a rhythm like that, whoa, 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 where you're, and a sound, a note that your ear will hear, is just a difference in frequency. As you can see there, the human ear can hear between 20 hertz and 20,000 hertz. So those are much higher. Even at the low end, 20 hertz is very, very quick. You can't clap 20 claps a second, I assume. As you speed up a whoa, 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 at some point, it stops sounding like a wave and starts sounding like just a note, just a frequency in your ear. But anyway, that's a little piece of acoustics for you. So, but suppose just at the level of, okay, I can make different, low sounds and high sounds. What sound should we make? What frequencies, what notes should we play that sound good together? And we start with just a little piece of information from Pythagoras. Notes sound good together when their frequencies are in small whole number ratios. So the story goes, and it might be apocryphal, but never mind. Pythagoras was heard two anvils being hit at the same time with a hammer, and one was twice the size of the other one. And the two notes that they were making, the tinging sound, sounded good together, sounded harmonious. And so this was what led him to sort of realize this. So, okay, which notes should we play? We're starting from scratch here. We're assuming you've never seen a musical instrument. Well, let's have a look at some small number ratios. So in this little table here, as you go down, the first number changes, and as you go to the right, the second number changes. So there's some small number ratios for you. Of course, like for example, 1 to 1 and 2 to 2 and 3 to 3 are the same ratio. So let's get rid of all the repeated ones, like 1 to 2 and 2 to 4 and 3 to 6 are the same ratio. So when we do that, we've got these ones, and we're not really at this point caring about the order. So 1 to 2 and 2 to 1 and 2 to 1 and 1 to 2, 3 to 1 and 1 to 3. So actually we only need the sort of the bottom half of this. Okay, so if I'm playing a note, it will sound good if you play a note, you make a sound with a frequency that's one of these small number ratios of the one that I'm making. And as a starting point, whether we're making those sounds one after the other, melody, or we're making them at the same time, harmony, this is a good place to get started. So, all right, how are we going to pick the notes? What frequencies, what hertz do we want?
Can I jump in and ask another stupid question?
Go for it.
Is this universally agreed? Would every person on the planet say that sounds where with these ratios are good, or
generally yes? The question is how much. When you want to do something a little bit more complicated, different cultures. I'll get to this a bit more at the end. Different cultures will choose the frequencies a bit different, and so when you start like you don't want all the sounds to be nice. Sometimes you want some tension, or you want some sadness, or you want to invoke a bit of dissonance in there as well. And it's how you choose those ones where actually most of the difference is. But generally, as a general rule, at least the first couple of ratios here are reasonably universal, like the 2-to-1 and 3-to-2, for example. Okay. Here's a way we could construct the set of notes that we want. Suppose we have 3 wishes. Here's the first one. Right, we've got between 20 and 20,000 hertz to pick our frequencies from. We want a finite number of notes. Right, so if we build a piano, there's only a finite number of buttons there. So that seems an obvious one. Here's another one. For any notes that we choose, let's pick the simplest ratio, which is not just 1-to-1, say 1-to-2 or 2-to-1. Now, looking ahead a bit, that's called an octave, but we'll see why that is later. For each note, the notes with a ratio of 1-to-2 and 2-to-1 are also notes. So if there's a button on the keyboard that hits a note, I can go up an octave to the one that's twice the frequency, and I can go down to half the frequency, unless I go off the edge, the edge of human hearing, and then that's what makes it finite. So that seems a reasonable thing. In particular, what that does is, if we look at the whole range of frequencies we could choose from, if I just choose frequencies, notes in a range between some number and double that number, suppose I just choose these ones, where that's double that. If I then want the notes over the rest of the range, I just copy and paste that little set out to the ends, and that's all my notes. There can't be any other ones, otherwise I could just double them back into this range. That make sense?
Yes.
Good. Okay, 3 wishes. Here's the third wish. So I've got this ratio of 2-to-1. Let's think about in what is, in some sense, the next simplest ratio. You could say 3-to-1, but that's sort of outside the range of between 1 and 2. Or we could say 3-to-2. That's nice and inside the range. So we could say for each note, the other notes with a ratio of 2-to-3 and 3-to-2. For various reasons, again, this is called a fifth, confusingly. But that 3-to-2 ratio, that's always available as well. So if I hit a note on my piano, I can always find one that's another note, which is a ratio of 3-to-2 and a ratio of 2-to-3. So I can go up a fifth or down a fifth. And the problem is, even at this level of simplicity and abstraction, even with all the complexities of, are we sure about this Pythagoras stuff and all of that, even at this simplified level, this wish list is inconsistent. We cannot possibly choose frequencies in that range, a set of notes that obey these 3 principles. So here's the reason. Suppose you start with some frequency, just pick one in the middle anywhere. Well, I'm allowed to go, and we're going to choose ones between that starting note and double that starting note for the reasons we saw before, because that's the octave. Okay. So start at the starting note, and I'm allowed to go up by that ratio of 3-to-2, a fifth. Okay, so I go up by 3-to-2, and then I've got a new note. Hooray! We're off and racing. And then I'm allowed to, via the third, wish list, point in the wish list, I can go up again another 3-to-2, which gets me to 9-to-4. But that's outside the octave. But what I could do then is just jump down a factor of 2, and I end up with this note. And so I got here with just fifths and octaves, so with a ratio of 3-to-2 and the ratio of 2-to-1, or the inverses of those. So that one's good. And I can just keep doing this. 27/16, 81/32. Whoops, that's outside the octave. Let's go down again. 81 over 64, 243 over 128. These aren't nice small number ratios. This is starting to look a bit suspicious. So the problem is I could keep doing this process forever. And the only way to not generate an infinite number of notes here is if miraculously somehow we landed back at the start and then the process would repeat itself. So every note generated has a ratio to the starting note of the form 3 to the power of something to 2 to the power of something. But for the sequence to repeat, we have to arrive back at the starting point, 1 to 1. And there's no way that 3 to the power of something to 2 to the power of something is ever 1 to 1. But 3 to the power of something is always odd, 2 to the power of something is always even, so that they're never going to be equal. So we're never going to get the ratio 1 to 1. So this is why music theory, even at this most basic level, immediately throws you a curveball. We have the most 3 obvious wishes that we want here, and they're inconsistent with each other. And so the trick now is, what do we do? Something's got to give. What do we actually do to sort this out and actually choose some notes to put on our piano or our instrument or whatever, so that we can actually start to play something? All right. Here's one option. And I say one option because I'll go through some other options later. Here's by far the most common option today. The one that's used for a piano, the one that's used for a guitar. If you pick up a random instrument today, it's using this option, but it's only one option. But so here's the idea. We can't really mess with A unless we want to make an infinitely large piano. And B, the ratio of 2 to 1 is so basic that we don't really want to mess with that too much. But so C's got to change. And so what we do is, instead of having the ratio of 2 to 3 and 3 to 2, we do almost those ratios. We make ourselves an almost a fifth. And so we don't exactly have those ratios. So for every note, other notes with almost a ratio of 2 to 3 and 3 to 2 are also notes. Does that make sense?
Yes.
Okay. So if we think about what we did before, that whole process of go up by the ratio of almost 3 to 2 and then back down by a ratio of 2, so up by a fifth, down by an octave if we need to, it must be the case that some number of almost fifths makes n octaves. Here's the equation we need to solve. We want to go up and down by the factor of 3 to 2, but that doesn't make a neat even number of octaves. So what we do instead is we want to approximate 3 over 2 by 2 to the power of something. 2 to the power of something where we've got some whole numbers here, where n over and m are both whole numbers. Because then if I go up m times, just go this thing times by itself m times, that's then this thing to the power of m. And if you know your indice rules, the m's cancel, and that's 2 to the n, which is some whole number of octaves. And hey presto, we've solved our little problem. So we want to find a rational approximation here. There's a lovely way to approach this, which involves something called continued fractions, but I don't really have time to go into that. I'll put a link to I did a blog post on this a while ago. What we could do is just go through small values of n and m just systematically and try to work out which ones almost work here. So from the small numbers, the first one worth noting is if we let m equal to 5 and n equal to 3, 2 to the power of 5 over 3 is that, which is kind of roughly 1.5, but not quite. That's large enough that the human ear can tell the difference between 1.516 and 1.5. As a general rule, so I'm told, about a 5% difference is enough for human beings to hear. If I play a note and then pause and then play a note that's 5% different, if you've got decent musical ears, you'll be able to hear that one is different. So that's a bit too big. We let m equals 12, n equals 7, 2 to the power of 7 over 12. That's pretty good, actually. That's smaller than the human range. And if we wanted to do better than that approximation, we'd have to go all the way up to 41 over 24. Now remember, every time when we did our little experiment, when we went up by that factor of 3 over 2, or almost 3 over 2 in this case, every time we did that, we generated a new note. So M here, the number of times you have to go up, that's how many notes there are in the scale. And 5 is not a lot, and 41 is a lot, but 12, that's kind of useful because they're not too widely spaced, but they're not so crammed together you couldn't really tell the difference from one note to the next. So this middle one is the way that we go. This is what the musical scale of almost all Western music has been based on for the last couple of 100 years. The fact that 3/2 is roughly equal to 2 to the power of 7/12. If we then do our little experiment of going up by the 5th and then down when we need to, the powers of 2 that we get is if we start at 2 to the power of 0, which is just 1, we go up to, remember, 7/12. And then if we multiplied it by that again, we would get 14/12, 2 to the power of 14/12, but that's outside the range. So we go down by a factor of 2, which makes 2 to the power of 2/12. Anyway, keep doing that, and you get this sequence of numbers: 7, 2, 9, 4, 11, 6, 1, 8, 3, 10, 5, 12, which might seem a bit random, but we'll see that actually they're extremely useful. The fact that there's 12 of them and there's a finite number and they sort of go around in a circle suggests that actually we should put them on a clock face, and then we might be able to see some useful things. So here they are going around a clock face, just for some fun. These are arranged by these intervals of the almost fifth that we've been talking about. We could rearrange them in order of frequency, and what we just get is this. It's just all the powers of 12. From whatever starting point, the next note up in frequency is 2 to the power of 1/12, and then the next one is another power of... So the basis here is what's called a semitone, and the ratio of the frequencies is 2 to the power of 1/12. The most famous number in all of music theory, if you're into it. Let me do a couple of quick things with this, and then I'm sure you've got some questions, and we'll try to patch those up. If we look at most... Now, again, we're making a choice here. We're not doing something universal. We're doing something specific, something that Western music has done and some other, music elsewhere in the world has done, but not all. We can look at the major scale. So if we take these notes, there's a subset of those notes that tends to sound good together. And if you're familiar with the song Do, Re, Mi from The Sound of Music, those are the notes. So the whole point of Do, Re, Mi is it's a scale. Do, Re, Mi, Fa, Sol, La, Ti, Do, or in tune if you like. So she's teaching them that scale, and those are these ones. So we start with some starting note, and then we go for 2/12, 4/12, 5, 7, 9, and 11. Now, there's no deeper reason for that other than we played it and it sounded good. But if we map that over from the let's go in order of frequency to the let's go in order of fifths over here, something kind of interesting happens. As they map over, they all map over to one side. So that sort of gives a clue about what's happening here. Over here, if you're next to this one, you're sort of close together in frequency. Over on this one, on the left-hand side, if you're close together, you're sort of close together musically, in a sense. I'll explain that a little bit more. If we do this, if we start at the note that's usually called C on a piano, these notes are all the white notes, and the other notes are all the black notes. And so we actually give these names, C, D, E, F, G, A, and B. I don't know why that's what happened, but it did. And then
probably named by an astronomer.
That sounds about right. No, there'd be some stupid acronym. Anyway. The ones in between are then either something sharp or something flat. So D sharp, E flat are the same note. If we then take these names and then do that same mapping over to this side, we get this arrangement, which looks random and weird. I mean, as I said, all the named notes are over on one side. What that tells you is the C major scale is all sort of together. This is a very famous thing called the circle of fifths. which is super important. Let me give you a couple of applications. We've talked about playing two notes together. Very often we want to play more notes together. So here's a basic way that we could do that. Suppose we start with a piano keyboard. So all the notes I've been talking about in the major scale are all these white notes starting on C, C, D, E, F, G, A, B, C again. We could play three notes together as follows. We could just do one note and then skip one and then the next one and then skip one and then the next one. So starting from C, we'll go C and E and G. That's a pattern we might want to look at and listen to. And it turns out that's what's called a major triad. It sounds happy and it's arriving. It's very triumphant. Notice that from C, if we count all the notes in between, we go 1, 2, 3, 4 to get to the middle note, and then 1, 2, 3 steps to get to the higher note. All right, let's do that again, but starting on D, D, F, and A. This has a slightly different pattern. So D, 1, 2, 3 to get to the middle note, and then 4 steps to get to the upper note. This is a minor triad. This is what you play when the bad guy walks into the bar. You know, mystery and sadness and tension. And so we get a pattern here of we had a major one and then we get a minor one. And just to give the answer, we then get a minor one and then a major one and then a major one and then a minor one. And just to be weird, the last one goes 3 steps and then 3 steps. That's called a diminished chord, but never mind. If we go back now to our circle of fifths, we find all the major ones ended up close to all the major ones ended up near the home key. So this is all, you know, happiness and lightness and we're all home and safe and nice up here. And then the minor ones all ended up a bit over to the side, a bit further away, a bit more mysterious. And then the weirdo diminished one ended up almost right way around the other side. This is so common that actually we rename these chords. Remember, because we've got a circular symmetry here, if you want to do all of this in another key, just take everything here and start to twist it around. So if you take the circle of fifth and just turn it, you'll put G up the top, and then everything else just fits. Just change all the labels and you'll get how to play the thing in G major instead of C major. So within a particular key, it's very useful just to refer to each of these by the number they are in the major scale. So C is 1, and then the next note is D, so that's a 2. And jumping ahead, these are them. So 1, 2, 3, 4, 5, 6, and 7. And this is very commonly how musicians refer to these chords, so much so that it turns up in songs. So if you're familiar with Hallelujah by Leonard Cohen, you'll know there's a secret chord that David played in Please the Lord. Are you familiar with this?
It goes like this, the 4th, the 5th.
It goes like this, the 4th, the 5th, the minor fall, goes out to the 6th minor, the major lift, the baffled king, composing, and just to throw in a curveball, he then goes to the 3rd and then back to the 6th. So it goes like this, the 4th, the 5th, the minor fall. You notice there's a nice 4, 5, 6 transition there. At the very end, he wants to go back to the minor chord just so it's nice and mysterious at the end, but he wants to feel that sense of resolution. So in the circle of fifths, if you go anti-clockwise, it feels like going home. And if you go clockwise, it feels like going away from home. So he wanted to go home, but to a minor chord. And so he jumps all the way out here so he can then go home, but to a minor chord. Now, someone's going to comment in the comments, so I'll just get ahead of them. In fact, he uses a major third, not a minor third. But anyway. There's a wonderful video I'll link to from a music producer who has a YouTube channel called Rick Beato, who listens to the top 10 pop hits for the first time just to see what's going on. And all he does is he listens to about the first 10 seconds and then calls out what the progression of the chords is. So he just listens to 10 seconds and then goes, okay, that's 1, 4, 6, 5. And then he goes to the next song and go, okay, that's 1, 2, 3, 5. He just calls out these. So in all the top 10, these were all the chords he ever needed, except actually for this major third that also Leonard Cohen uses. So that's pop music. This is all of pop music here. If you forget the diminished, it's the weirdo. If you nail those 6 chords, you can basically play anything. If you're on a guitar, if you can play those in any key, you've basically got all the songs. If you want to be a bit more adventurous, remembering that going this way is sort of going home, if you've got something which is a bit more jazz, wants to get a bit more further away from home. So if you know the song Moon River from Breakfast at Tiffany's, is that?
I do.
Yes, good. There's a nice bit at the end of the verse where, just to get that lovely progression home, the chords jump all the way over to here and then just step all the way back.
Wherever you're going, I'm going your way too.
And so you just go halfway around. And so that's a way of not just staying in the nice pop safe bit over here, but actually making a more interesting progression that feels like it's going somewhere. And if you're a total jazz nut, then you can do what the jazz saxophonist John Coltrane did in a famous song called Giant Steps, where he wanted to just totally break out of any sort of, let's do things nice and safe. What sort of pattern could I draw on here that just gets me into the weirdest areas the fastest? And so from any chord, if you jump straight across, that's sort of the biggest jump. That's called the tritone. But then if you jump that way again, you just get back where you started. What Coltrane did was basically do this jump in his song called Giant Steps. Playing music on YouTube's a bit dodgy. You'll get banned or whatever. So I'll leave people to go and look up Giant Steps. But basically, in very quick succession, the opening jumps in this triangle pattern just to get out into the weirdest bits. So it's, jazz, right? So just to finish off, we made a choice there at some point. Given that we couldn't do this, the wish list is inconsistent, we put almost ratios of 3:2. And if you look at the ratios that we actually get, so 2 to the power of 1 over 12, 2 to the power of 2 over 12, these are all the ratios you get. And the weird thing is we wanted nice whole number ratios, and we got, at the end of that, none of those. None of these are nice whole number ratios except for the octave, which is a bit weird. I mean, we chose it so that this fifth is almost 3 over 2 to within 2%. So that's not bad. But all the other ones, to some various degree, are away from what sort of sounds like the nearest whole number ratio, and sometimes by 14% in the case of the major third here. That's noticeable. And actually, once you start to hear this, it's really weird. If you again, go look this up. If you just play the boring old major chord that you've heard 1,000 times before, and then have someone play it where instead of what's called equal temperament that we've been using, you use the simplest ratio instead, suddenly you realize that chord has had beating in it, sort of the pulsing that you get when two frequencies are close to each other in it the whole time, but you didn't hear it because you weren't used to it. So that's kind of weird. Here's two other options we could do. There's something called the Pythagorean scale. Rather than saying that every note has almost a fifth, we instead say almost every note has a perfect fifth. So you start from the first and you go a perfect fifth, perfect ratio of 3 over 2, and then you do it the other way around, and then they're not going to meet up at the other side, but you just sort of you bend these 2/5 a bit in some weird way, and you try to hide all of that weirdness that we tried to spread out. The previous example sort of spread that out over everything, so everyone gets an imperfect fifth. This, you try to hide it away on one particular part of the circle of fifths. The thing about that is you've lost that circular symmetry. So all of the different keys aren't the same now. They don't have the same relationships. But, at least all your fifths sound nice, and actually your thirds and sixths will sound good as well. Another option is to just say, well, forget all of that. Let's just use these ratios. Whatever key we're in, let's just use those ratios. This is called a just intonation. And I'll finish on this. The weird thing I've been learning is I grew up playing the piano, where you just go and hit buttons on a keyboard and who cares? Like, someone else tunes it. You don't even tune your own instrument. In the last couple of years, I've been learning the cello. In the cello, you actually have to play, it's recommended that you play in all three of these different tunings. So there's no frets. You can play any note you want. It's a continuous scale there. And so what the standard thing for a cello player, when you're good, not like me, who's rubbish, is you play in the just intonation if you're playing more than one note at the same time, so you get the nice ratio between the notes. You play the previous one, the Pythagorean scale, when you're playing a melody, one note after the other. And if you're playing with a piano that's tuned in the equal temperament, the one I was talking with, the almost fifths, then you better play along with that, the piano, because they're not changing. I mean, the piano is just what it is. So you have to actually learn to have a good enough ear to play in all three of these different scales. Beyond that, elsewhere in the world, we made some arbitrary choices here. Elsewhere in the world, they have made different arbitrary choices. And so you get different scales in different part of the world. Once you have this sort of scale where you just choose some nice ratios and go for it, there's no reason to have 12 notes anymore. And so in parts of India, for example, there are musical scales with 22 notes in them for whatever reason they came up with. So this is a very particular, this is how we did it. This is not the music theory. This is a music theory that if you're familiar, if you have Western ears, you're familiar with, but other places in the world do it differently. And that is my far too quick and probably confusing introduction to music.
Okay, I'm going to ask a question.
Hit it.
We should probably finish up before too long because we've been going on
We have been going on.
Is this all after the fact? Did the people who designed the piano think about this theory, or did they build the piano and then afterwards somebody came and retrofit in this kind of picture?
So this is where, this is really interesting. Before the piano, it's basically the one I've got on screen now, the just intonation that most people are using. You just play, especially if you've got like string quartets, they use just intonation all the time. It's really it's the piano that inspires the development of equal temperament so that you can play the same in all keys. So that you don't have to, if you're a string quartet, whatever key you're in, you can pick these ratios. You can change the notes according to what key, we're going to play this one in E flat major. All right, we'll just do these ratios in E flat major. You can't go changing the tuning on your piano every time they change the key of the song. So yeah, it actually, the piano is one of the major reasons why, because you've got this great big thing that needs to be tuned by an expert and it takes like 2 hours or 3 hours, why actually equal temperament came to be the dominant tuning. So it's around about the same time that these two things get developed. The history is actually really interesting.
Okay, I think I've learned something. I'm not sure what it is, but I do like the relationship between mathematics and music. Let's try and find some other topics to talk about in the future.
Yeah. So the main point here is actually, if you have been on this channel for a bit, you've got a bit of a mind for physics, you like a little bit of math. There was nothing here that, this is all just to the power of. If you can handle that, dig into some mathematics of music. It's really wonderful.